Today's topic is absolute scale of temperature. Efficiency of Carnot's ideal reversible engine depends only on the temperature of source and temperature of sink, and it does not depend on the nature of working substance. On this basis, Kelvin considered a scale of temperature which does not depend on the nature of its working substance. This is known as absolute scale of temperature, or the thermodynamic scale of temperature, or Kelvin scale of temperature. Consider a Carnot engine which is working between source of high temperature θ1 and sink of low temperature θ2. This extracts heat Q1 from source of high temperature and rejects heat Q2 to sink of low temperature and converts remaining heat, which is Q1 minus Q2, into work. Efficiency of this engine will be given by eta equal to 1 minus Q2 upon Q1, and this efficiency will be function of temperature of source and temperature of sink. If temperature of source and temperature of sink are θ1 and θ2, then this efficiency will be equal to F θ1 θ2, where f is some small f is some function of θ1 and θ2. Here θ1 and θ2 are temperatures on arbitrary scale of temperature. From this relation we have Q2 upon Q1 equal to 1 minus F θ1 θ2, and from this relation we can get Q1 upon Q2 equal to 1 upon 1 minus F θ1 θ2. Now we write 1 upon 1 minus small f θ1 θ2 as equal to capital F θ1 θ2, which is new function of θ1 and θ2. So we have ratio of two heats Q1 and Q2, and it is equal to function capital F, which is function of θ1 and θ2. θ1 and θ2 are temperatures of source and sink at arbitrary scale, and in left hand side we have ratio of two heats. Q1 is heat extracted from source and Q2 is heat rejected to sink. Now if Carnot engine is working between temperatures θ2 and θ3 and extract heat Q2 from source of high temperature θ2 and rejects heat Q3 to sink of low temperature θ3, then we have, as equation 1 we can write now Q2 upon Q3 equal to F θ2 θ3. And similarly for Carnot engine which is working between temperatures θ1 and θ3, we can write Q1 upon Q3 equal to F θ1 θ3. So we have three relations. Relation 1 is this: Q1 upon Q2 equal to capital F θ1 θ2. Second is Q2 upon Q3 equal to F θ2 θ3. And third is Q1 upon Q3 equal to F θ1 θ3. If we multiply left hand side of first two equations, that are Q1 upon Q2 and Q2 upon Q3, we multiply these two, then we get Q1 upon Q2 into Q2 upon Q3, and this will be equal to Q1 upon Q3. Q2 will cancel out. Now substitute the values of Q1 upon Q2, Q2 upon Q3 and Q1 upon Q3 from first three equations. In this equation, if we substitute these three values, then we get this relation F theta 1 theta 2 into F theta 2 theta 3 equal to F theta 1 theta 3. We write this as equation 4. Equation 4 will be satisfied only if the function f theta 1 theta 2 has this type of form. This relation 4 is satisfied only when function capital F have this type of form. Capital F theta 1 theta 2 is equal to phi theta 1 upon phi theta 2, where phi is another function of theta. Now F theta 1 theta 2 is Q1 upon Q2. So we have Q1 upon Q2 equal to phi theta 1 upon phi theta 2. Now temperature theta 1 is greater than theta 2 and phi theta 1 will also be greater than phi theta 2 because Q1 is greater than Q2. So from relation 5 we see that phi theta 1 will be greater than phi theta 2. Now we see that theta 1 is greater than theta 2 and phi theta 1 is greater than phi theta 2. So we see that when temperature theta increases, this function phi theta also increases. So phi is such function of temperature theta, value of which increases with increase in temperature. So this function can be used for temperature measurement. If phi theta represent the temperature tau on new scale of temperature, then from equation 5 we can write Q1 upon Q2 equal to tau 1 upon tau 2. We write phi theta 1 as tau 1 and phi theta 2 as tau 2. These are the two temperatures on new scale. So we see that temperature on this new scale, ratio of these two temperatures in new scale will be equal to ratio of these two heats, Q1 and Q2. Q1 is the heat extracted from source and Q2 is the heat rejected to sink. So ratio of two temperatures that are now tau 1 and tau 2 is equal to ratio of two heats Q1 and Q2. Here tau 1 and tau 2 are absolute temperature or Kelvin temperatures. These are temperatures on new scale, that is known as Kelvin's absolute scale. These are corresponding to temperatures theta 1 and theta 2. Tau 1 and tau 2 are absolute temperatures corresponding to the temperatures theta 1 and theta 2. So according to Kelvin's scale of absolute temperature, ratio of two temperatures measured on absolute scale is equal to ratio of heat extracted to heat rejected by Carnot engine acting between these two temperatures. In this way, in this new Kelvin's scale, we can define the ratio of two temperatures, tau 1 and tau 2, and this ratio is equal to Q1 upon Q2. Now we define 0 on absolute scale. Efficiency of Carnot engine acting between absolute temperatures tau 1 and tau 2 will be given by this relation eta efficiency, which is equal to 1 minus Q2 upon Q1 is now equal to 1 minus tau 2 upon tau 1, as Q2 upon Q1 is equal to tau 2 upon tau 1. So this efficiency eta will becomes 1 only when tau 2 is 0. So when tau 2, temperature of sink, is 0, then efficiency of this Carnot engine will becomes equal to 1, that is 100%. So now we can define 0 on absolute scale. 0 on absolute scale of temperature, and it is known as absolute zero temperature, and it is that temperature of the sink for which efficiency of reversible Carnot engine is 100%, that is 1. In this way we can define absolute zero temperature or 0 on absolute scale. It is the temperature of sink tau 2 for which efficiency eta becomes 1. Now we see that negative on this absolute scale temperature is impossible. If we take tau 2 as negative in this relation 7, then we find that efficiency eta will becomes greater than 1. It is 1 plus something. So which is not possible. Efficiency of Carnot engine which is greater than 1, greater than 100%, it is not possible. So negative absolute temperature is also not possible. Now we define size of degree on absolute scale of temperature. To determine the size of degree on absolute scale of temperature, we divide the interval of steam point and ice point. We write steam point, which is temperature of steam, as tau steam, and ice point, which is temperature of ice, we write it as tau ice. And this difference of these two temperatures, steam point and ice point, difference of these two temperatures, we divide it into 100 equal parts as in Celsius scale of temperature. That is, we write tau steam minus tau ice equal to 100. If this difference is divided into 100 equal parts, then each part represents 1 degree Kelvin temperature difference. So in this way we can define 1 degree Kelvin on this new absolute scale or Kelvin scale. Indicator diagram for Carnot engine acting between steam point and ice point is shown in this figure. This is indicator diagram, that is PV diagram, for a Carnot engine which is working between steam point, that is tau ice, and tau steam, and ice point, which is tau ice, and it extracts heat Q stream from source of temperature tau steam, and it rejects heat Q ice to sink of temperature tau ice. The work done by this Carnot engine will be equal to the area of this curve. So area enclosed by Carnot cycle represents work done in that cycle. So Kelvin, 1 degree Kelvin, is the difference in temperature of source and sink between which a reversible engine yields 1/100th part of work which is obtained from reversible engine working between the steam point and ice point. 1 degree Kelvin will be the difference in temperature of source and sink for which work done is equal to 1/100 times the work done by this Carnot engine which works between tau steam and tau ice. In this way we can define 1 degree Kelvin. Now to determine unknown temperature, we consider a Carnot engine acting between steam point tau steam and unknown temperature tau, and it is extracting Q steam heat from source and rejecting Q heat to sink. Then we have Q steam upon Q equal to tau steam upon tau. Now this Carnot engine is working between two temperatures on absolute scale, that are tau steam and tau. Tau steam is steam temperature and tau is unknown temperature. So the ratio of these two temperatures will be equal to the ratio of these heats, that are Q steam and Q. Q steam is heat extracted from source of temperature tau steam, and Q is the heat rejected to sink of temperature tau. Similarly, for engine which is working between unknown temperature tau and ice point tau ice, we can write Q upon Q ice is equal to tau upon tau ice. We consider another Carnot engine which is working between these two temperatures tau and tau ice. This ratio tau upon tau ice is equal to Q upon Q ice. Here Q is the heat extracted from source of temperature tau, and Q ice is the heat rejected to sink of low temperature, that is tau ice. If we invert this relation, we find that Q ice upon Q equal to tau ice upon tau, and if we subtract equation 9 and 10, we find this relation. Q steam minus Q ice upon Q equal to tau steam minus tau ice upon tau, and tau steam minus tau ice is 100. So right hand side is equal to 100 upon tau, and from this relation we can find expression for tau, which is unknown temperature. So unknown temperature tau is given by this relation. It is Q upon Q steam minus Q ice into 100. In this way we can determine unknown temperature tau on this new absolute scale of temperature. Now we prove that this new absolute scale of temperature is equivalent to perfect gas scale. In perfect gas scale, we write temperatures by capital T, and in this new scale of temperature, that is Kelvin's absolute scale of temperature, we write temperatures by tau. So we will now prove that these two temperature scales are equivalent or the same. To prove this, consider a heat engine which is working between source and sink, whose temperatures are respectively T1 and T2, capital T1 and capital T2 on perfect gas scale, and tau 1 and tau 2 on absolute scale. If engine extracts Q1 heat from source and rejects Q2 heat to sink, its efficiency eta will be given by eta is equal to 1 minus Q2 upon Q1, and this efficiency is equal to 1 minus T2 upon T1, because Q2 upon Q1 is T2 upon T1. T2 and T1 are temperatures of sink and source respectively, and these are the temperature on perfect gas scale. Also, this efficiency is given by 1 minus tau 2 upon tau 1. Here tau 2 and tau 1 are temperatures on new Kelvin's absolute scale of temperature. So this Q2 upon Q1 is also equal to tau 2 upon tau 1. So efficiency eta, which is 1 minus Q2 upon Q1, is equal to 1 minus T2 upon T1, and it is also equal to 1 minus tau 2 upon tau 1. Capital T are temperatures on perfect gas scale, and tau are temperatures on Kelvin's absolute scale. So from this relation we find that ratio of two temperatures T2 upon T1 is equal to tau 2 upon tau 1. So ratio of two temperatures are same in both the scales. One is perfect gas scale and other is Kelvin's scale or Kelvin's absolute scale. From equation 12, this is equation 12, which shows the ratio of two temperatures in the two scales are same. From this relation, it is clear that ratio of two temperatures are same on both scale. Let steam point and ice point on perfect gas scale are T steam and T ice respectively, and for absolute scale these two temperatures are tau steam and tau ice. Then we have T steam minus T ice is 100 steam temperature and ice temperature. Difference of these two temperatures is divided into 100 equal parts. So T steam minus T ice is 100, and also in Kelvin's absolute scale this difference is also equal to 100, that is tau steam minus tau ice is also equal to 100. Now from this relation T2 upon T1 equal to tau 2 upon tau 1, we can write T steam upon T ice equal to tau steam upon tau ice. If we subtract 1 from left hand side and right hand side, we get T steam upon T ice minus 1 equal to tau steam upon tau ice minus 1. If we solve this equation, we get T steam minus T ice upon T ice equal to tau steam minus tau ice upon tau ice, and the difference of these two temperatures in numerator of both left hand side and right hand side are equal to 100. So we put this numerator equal to 100 on both the sides. We get 100 upon T ice equal to 100 upon tau ice. 100 is cancel out and we get T ice equal to tau ice. So temperature of ice is same in both the scales. In perfect gas scale it is capital T ice, and in Kelvin's absolute scale it is tau ice. If we put T ice equal to tau ice in equation 15, we get T steam equal to tau steam. So we see that ice temperatures are same and steam temperatures are same in both these scales. From equation 16 and 17, it is clear that steam points and ice points are same in both scales. Now if we consider a reversible Carnot engine which is working between steam point and some unknown temperature, value of which on perfect gas scale is T and that on absolute scale is tau. Now we consider a Carnot engine which is working between steam point and some another temperature, and this another unknown temperature we write it as capital T in perfect gas scale, and we write it by tau on absolute scale. Then we can write T steam upon T equal to tau steam upon tau. From this relation T2 upon T1 equal to tau 2 upon tau 1. We can write T steam upon T equal to tau steam upon tau, and as T steam is equal to tau steam, so it is cancelled out and we have T equal to tau. So any unknown temperature, value of any temperature in both the scales, in perfect gas scale or in Kelvin's absolute scale, value of any temperature remains the same. So value of temperature on perfect gas scale and absolute scale are same in both temperature. So both temperature scales are equivalent. Perfect gas scale and Kelvin's absolute scale, these two scales are equivalent as any temperature is same in both these scales.